So let's now consider the forces which are acting upon this mass which is hanging on the end of a spring here. Now Newton's first law tells us that since this mass is not moving, there can't be any unbalanced forces acting upon it. Now we know that this mass here has a weight force which is pulling it down and is given by mg. So this tells us that this spring must be exerting an upwards force on the mass which has the same magnitude as the weight force. So we can work out the amount of force that a spring applies to a mass attached to it using something known as Hooke's law. So Hooke's law applies to many but not all springs. So Hooke's law can be written as the force F is equal to minus K times D. So in this equation, F is a vector and it's the force given in newtons. K is the spring constant, which is sometimes known as the stiffness constant, and it's different for different springs. D is the extension of the spring from its equilibrium position, and it again is a vector. Now the negative sign there is important, and it tells us that the displacement is in the opposite direction to the force. So in this case, when I hung the mass from the spring extended downwards, but the force that the spring is applying to the mass is an upwards force. So those are always in opposite directions. So let's have a go at an example problem now. So the question, when a 200-gram mass is added to a vertical spring, the spring extends 10 centimeters. Assuming that the spring obeys Hooke's law, what is the spring constant of the spring? How far would it extend in total if an additional 300 grams were added? Okay, so to answer this one, we're going to need to make use of Hooke's law, which tells us that the force is equal to minus the spring constant times the distance which it is extended. So we're asked, first of all, to find this spring constant K. So we can write, well, K is equal to, let's ignore the negative sign and the vectors. So let's put our absolute value sign. So we'll put the absolute value sign around F, and we'll also take the absolute value of the minus D, which is just D. So we know that if we take the force acting upon the spring and divide it by the distance it was extended, we'll end up with a spring constant. Now in this case, because it's vertical, the force which is acting upon it when the mass is added is just going to be the weight force. So the size of this force is going to be mg, and then we need to divide it by the distance it extends. So now we can substitute in. We know it's a 200-gram mass, so let's use SI units. So that's 0.200 kilograms, and we know that G is 9.8. And then we'll want to divide by the distance which it extends, which is 10 centimeters. So in SI units, that's 0.10 meters. And so solving this on the calculator, I get 19.6 newtons per meter. Now in this question, 200 grams is given in up to 3 significant figures, and 10 centimeters was given up to 2 significant figures. So I should just answer with 2 significant figures. So I'll say this is equal to 20 newtons per meter. And then in the next part of the question, it asks us to get how far it's going to extend. So now we need to know D if an additional 300 grams was added. So the total mass which has been added now was the 200 grams and then the 300 grams. So 500 grams or 0.5 kilograms. So let's rearrange Hooke's law here. And we've got, well, the distance that it extends is going to be equal to F divided by minus K. And we know that the weight force is acting down, and so the spring force is going to be acting up. So this force here is the spring force. So this is the upwards force here, and so it's going to move downwards because of this negative sign. So at this point, let's get rid of all of the signs and just put absolute values on everything. Okay, so the force which is acting upon it, it must balance that weight force. So it must be mg, and then we need to divide by k. And m in this case is the 0.500, This is times 9.8, and then we divide by K, the spring force, and we'll keep all our significant figures for our working, so 19.6. And so solving this on the calculator, we end up with 0.25 meters. So we could answer that way, or because the distance here was given in centimeters, we could say, well, that's equal to 25 centimeters.